And it's quite crazy.
And yes, yeah, and it's been pretty crazy. But I think we've actually answered most of the questions, the remaining questions on this generator. And we're going to need to do an update. But you were already aware of that. There's a couple of things that were overlooked, and with all the rushing. But we're gonna do an update, and we'll figure out what's the best venue to do that with. So I guess we could probably start with the questions, and the new information will become obvious, I think, as we answer the questions, and then we can summarize it after that. But it's really, I think, what we discovered today is that we've been thinking about a couple of things wrong, and it's really, how can I say? Patrick's going to say a few words. You all know who Patrick is, right?
Actually, what we are thinking is not wrong, because we're just seeing inside a box so far. But today, Jamie came up with a very crazy idea. You know why? Okay, here's the thing.
There's Patrick.
Now, since our goal output is 10 kilowatts, right? Hello?
Hello, right.
And if the output current is 40 amps and output voltage is only 230, but you can never get it. So today, Jamie decides to go outside the box, and let's say now we are gonna to up the end, make the output voltage goes to 1,000 volts times 10 amp. There we go. We got 10 kilowatts.
Yeah, that's basically it.
It's quite crazy, because I just checked the diesel generator on the shelf. The design output is just like 100 volts. So we're gonna output. What we're going to output is like 10 times more.
Mm-hmm. You mean, so this is actually outputting that much right now?
No, but we were going to do so.
Oh, okay.
Yeah, we've been thinking about it the wrong way. It's actually a high voltage generator.
Yeah.
It's not. It's the target was 10 kilowatts, and boy, everybody was thinking about this as a conventional sort of generator. If you go to the Lowe's and buy a generator, it's going to have a 240 volt output or 120 volt or whatever, and 10 amps or 20 amps, whatever you're buying. But we were trying to figure out why. Okay, we're only getting like 4.5 amps out of the thing, and it's resonating like crazy. And so where's the current? And we figured out today that it's working as it's supposed to work.
Yeah. It is designed to run at low current.
Yes.
It was the people on the other end that were wrong.
Yes. It's actually, well, when we built the prototype, when we were first observing it, when you find it, when you're close to the peak resonant frequency,
yes,
if you increase the motor speed even slightly, the voltage just shoots up. It starts going up like crazy. I've seen 500 volts on the output of this thing, and it kind of, I didn't want to go any higher because I was worried about insulation and things like that and arcing, but I was thinking, okay, well, how high does it go? And finally we figured out that it's actually working. We've got if you've got 5 amps and 2,000 volts, you have 10 kilowatts. it's a high
Look
voltage.
at Ed's face. You lit right up.
Iruka.
No, well, okay. What I'm thinking is that this is going to be generating several immediate questions from the group here. Is that?
Yes.
I mean, so look, people, if you've got questions, just put a question mark in the chat box so we don't all talk at once. But since I'm on here first, I'm just going to ask. So that output, is that then able to be turned into usable current?
You just need another transformer.
Well, you don't need it. You could do it that way.
Yeah.
There's a little bit of a challenge with the interface, interfacing the output. But like Patrick says, you could use a step down transformer. You know, you step down the voltage and step the current up. But you know, if you want to run an inverter right off the shelf, you can probably only go up to 600 volts or so. And you know, it all makes sense now because we were trying to figure out the tuning procedure a little better, and that the exciter coil, for instance, everybody's been having trouble getting the thing to resonate and to do anything. But if you have 230 volts across it, or 300, it's not across, it's in series. Even 300 volts, it's going to be very difficult to get it to resonate. But if you pump 600 volts through there, it's going to start resonating.
Yeah.
So the tuning procedure now makes sense, and you need to do a little bit of fine tuning to make sure that you're on the peak resonant point. But you know, that it was a little bit of a mystery why we weren't getting any more current out of it than about 5 amps. Well, we didn't. It's not optimized here yet, but you know, I can see the tuning procedure that probably the maximum current you can get out of the thing is maybe 10 amps, but maybe 2,000 or 3,000 volts at 10 amps is, you know, you got your power. So there's a little bit of an interface challenge. Myself, an electronics guy, I could see no big deal to build the input or to modify the input of the inverter so that it would handle 1,000 volts or even 2,000 volts DC. And you could do a transformer too if you needed to, you know, bring the current up and the voltage down. So really, it seems like everybody's just been thinking about this wrong. Yeah. It's not a high current, low voltage generator. It's a low voltage or a high voltage, low current, relatively low current. And it, you know, it all points to the core. The
Yes.
core is the key. You have to build it to be able to withstand up to 5,000 volts on the primary coils, and you know, the secondary is not that difficult. Even if you were putting out 2,000 volts, it's not nearly as much of an insulation problem as the primary. But
so
it's not a voltage generator. It's a high voltage generator, relatively high.
I wish we had the engineer types on here to ask the questions, but they're all out enjoying life right now. So the construction of the core then is the high insulation. The large amount of insulation is going to be required to withstand higher voltages.
Yes.
That's pretty much the construction procedure now.
Yeah. Otherwise, it will go arc. Like today, we have so many arcs, and it's quite a little bit scary.
Yeah. It's
like okay, when we got resonance and it's arcing. Unfortunately, we have use spark plug, so arc goes outside, but it's still quite scary. Like
we came up with a way to protect the core. Just use a spark plug across the capacitors, and you know, if your voltage goes up higher than where you want it, it'll just arc across the spark plug or spark gap. You know, you could build something, and it won't happen inside the core. But still, to maximize the design, the better you build that core, the more power you get out of this thing. It just, and really the challenge is the input is what we're calling the primaries. They're actually vibrating coils, or you can think of them as they physically resonate and cause the steel to vibrate. So the secondary is a lot less of a problem. In fact, it's probably fine the way it is. The design with the 10 gauge wire and 350 turns, it's you can't, at least in the U.S. you can't get that inverter duty wire in 10 gauge. They stopped making it at 12 gauge.
Oh yeah, you covered this before.
Yeah, and actually that's what Witz was using in their videos, is 12 gauge. And it would be, it would probably be good to overbuild it, but I don't think you really need to have the inverter duty on the output. Of course, it can't hurt, but it all adds up. That what we saw is, if you are fairly well tuned and you're in resonance and you're putting out power, as you try to increase the motor speed, what actually happens is you increase the power, because it tends to phase locks a bit when you're when you're on the main resonant point. It doesn't like to come out of that RPM.
Ha!
And
That's that's just like an instrument.
Yes. Yes. It does. It's not only an electrical resonance, but a physical resonance that tries to hold the RPM steady. And if you add mechanical energy with your motor speed control, you're actually adding power to the output, because it deepens the resonance.
Yeah. So, but then when you reach a certain point of power input, then it forces the shift.
Well, yeah. I mean, you can move the motor speed. Depending on how much horsepower you've got. You could probably even run it through resonance if you had enough horsepower.
Yeah.
But you want to go the other way, so you can minimize your motor current.
Right.
That's going to be your self-running situation. Is you keep your input power as low as possible, and then you can use all the rest of the output power.
So is your point of resonance now that you've reached to create this current output, is it the same RPM and capacitor settings as before?
No, it's actually, I think we published 1450 RPM. Get the little one, there we go. It's actually around 2400, 2500. And I'm very happy if it's under 3000. That's easy. That's not fast. Let me get the exact number here that we were at today. The capacitor value we came up with was 0.125 microfarad. It's not completely tuned yet, but that's going to be close. And that was 1,331 RPM. So you don't have to run it fast. And that's going to be very good for ruggedness and life, and so that was well, we got up to about 4.5 amps. We have some insulation problems with this core, and if we push it any harder, it starts to arc. So that points me toward building this core to withstand build it as good as possible. But the insulation system is very important, and the more voltage you can get the thing to withstand, the more power you can get out of it. And I could see a situation where we could scale it up easily, it clears up a lot of things.
Cool.
It just requires a little change in the way you think about it. It's not really a conventional generator. It's not high voltage.
Isn't that usually the case? it's how we're looking at it that's usually the problem. Yeah.
Yeah.
So just a quick question on output. So since the amperage is low and the voltage is high, does that mean it can only run certain appliances or have a certain use, or is that all rectified when you turn it into usable current?
Yeah, no, it's not limited.
Okay.
If you up to 600 volts, an inverter will do all that for you.
Okay, cool. So we've got the power we need to run our world. And,
yes.
Yeah.
We got a couple of electronics guys to redesign the input section on the inverter so it'll handle maybe 2,000 volts.
Okay.
And then the sky's the limit.
Yes.
And you could do a conventional transformer too, a step down transformer if you wanted to put in 1,000 volts or 2,000 volts and you want to get lower voltage but higher current. Just a standard transformer.
Oh, this is awesome. This is so cool.
Yeah.
Yes.
This is so much like the QEG too, because every step of the way since last October, everything is last minute.
Yeah.
Everything you're pushing and you can't get something and you can't get it, and then you think you're just gonna give up and
Eureka.
Damn. It's like who made life this way? That's the way it works, right? You got to come up against this huge problem before you change enough to get the right insight.
It required us to change.
She's designed to be a power plant.
Yep.
She's meant to be to power the whole world.
Yeah.
You can very large. You can replace all the nuclear power plants very soon because it is designed to generate high voltage. It's like, the way this shit is, it's going to be a power plant, and maybe in just a few years we're gonna have a resonance power plant. Because that is how she designed. Let's her destiny.
Yeah. Could you possibly get a little more excited there on your end?
Huh?
This is my son.
Yeah. I don't know. Does my humor translate into Taiwan?
Well, certain terms are unknown, but he's the ace, one of our ace translators.
Yeah.
Couldn't have done anything here
Thank
without
you.
him.
Yeah, really.
Hasta la vista, Wiz.
We'll be back.
Yeah.
Yeah.
Okay.
So, very good day. And that may change some of the questions, but
I think once. Okay. I don't. Let's see. Did you guys? Okay. So Steve said he had transmitted a couple of questions to you guys. Did what you just share answer all those questions, and it's not worth going through them?
For the first question about motor, I say yes, because in Taiwan, we are now using AC motor with frequency drive. That's how we.
Yeah, we are.
Well, I don't have the questions, so I don't know what they are, but I just wanted to make sure that they got addressed if they needed to be.
Is that Steve Sager or Steve and Lisa? I see.
Hello.
Hello, beautiful Torontos.
Welcome.
Steve Sager, can you unmute and address the questions that you put out?
Yeah, there's only a couple of questions. I'll just find them here.
Oh, yeah, those questions. We have those. We have them right here.
Yeah, there was only like 4 of them.
Yeah, we got them. Here you go.
Yeah, well,
just read them out and then answer them. And if they've already been answered, you don't have to go over it again.
Okay. Who wants to read? You want to read?
No, you can read.
Okay.
I'm just going to see if I can put it in the
Can I
chat
say
box.
yes? That's what we're using now.
I'm going to
Well,
put
yeah,
the
but-
question in the chat
Have to
box.
be careful.
So you all
Hasn't
have
been
it.
tested.
Yeah. Okay, that you do it.
Okay.
Oh,
Can the DC drive motor be any motor driven by any AC or DC current independent of the accumulator, which is the core, I'm assuming. If we use a AC or DC servo or any motor driven by a VFD supplied by mains power for experimental and tuning purposes, this would provide less complexity instead of concentrating on recycling power from the accumulator through inverters from the startup on the first build. Well, what we recommended was to use just a simple DC variable speed, permanent magnet DC motor with brushes and a variac. And the reason for using that is because there's no electronics, and there would be no delay when you do the when you go to self power the thing. If your inverter has enough hold up time, you could probably run any motor.
yes.
But you have to have you have to have voltage there for a few moments. We don't know exactly what that figure is yet, but we will soon. You have to have a little bit of hold up time, and an electronic drive kind of defeats that because the ones that I've tested, if you cut the input power, they just stop instantly. And that's less of a problem than when you go to restart them. There's a delay. If there's an electronic drive, it doesn't start instantly. So that's the reason why we recommended the variac and the plain DC motor.
Well, I got a little.
Yeah. So, but once you have your electronic system designed and you know what your target RPM or what your tuned RPM is, you can really use any motor. The problem is that you want to minimize the hold up time that you need. If that's making sense, because when you have to quickly switch over from your local power company power to the QEG power, is that you want to do that as quickly as possible. And so you need something. You can't self-power it without some electronics, something to give you some hold-up time. We've tried, I think the fastest way to try to do it, I had a rocker switch that it takes almost no time to switch over from one pair of poles to the other pair, and it wouldn't keep going. As soon as you drop the power out of the drive motor, you go out of resonance. So the key is to have a little bit of hold up time, and you can do that for development. The easiest way to do that is just with a variac and a DC motor, and then as you add electronics, the inverter does have hold up time. If you use an inverter on the output, that will give you the hold up time that you need to switch it over to self run. But it's very difficult to do naked without it, no electronics or anything to hold the voltage up. Because really all you have is wire and steel in the generator.
Question.
Okay.
What if you were to start it with a battery that was part of the system?
Yeah, that could be done. That's the target was to have no. Well, the target was to have no batteries, no windings on the armature, no commutator, no slip rings, just bearings. And a
Question number 2.
Okay.
Can I use flywheel?
You could use a flywheel. That's
a flywheel can save some magnetic dynamic power. If we kill a switch, it keeps running for a long time.
Yeah, that would help.
Yeah,
That's it.
use the flywheel as your pulley.
Okay. There you go.
Yeah, the
hold up time.
flywheel means even you cut off the power, it keeps running. In industry, if you have a nice or good quality of flywheel, if even you cut off the power, it can keep self running for about an hour.
Well, yeah,
Yeah,
that's a little extreme, but
yeah.
But
Okay, flywheel.
But would it keep running at the exact frequency required to keep it going?
Just see.
We'll
well,
see.
it could slow down a little bit.
Yeah.
Depends whether you're.
Don't worry, because it would just need a little short time for the self power. So
Yeah.
don't worry. Don't worry. Try the flywheel. Flywheel.
Hey,
Yeah,
I'm going to let you guys figure that one out.
We can put flywheel and let our Taiwanese engineers think about. Okay, we can try flywheel, and even we cut off power, it keeps running and running and running.
Yep, we could try that. Yep, it's a good idea.
Yeah,
Just
it's only
need to
mechanical,
keep
right?
it spinning.
Keeps spinning.
And there's some time. It'll slow down a little bit. Depends where you are in resonance. If you're right at if you're just at the threshold of resonance, that probably wouldn't work. But if you're in the middle of your power band, it may be enough.
Because the resonance tends to hold it anyway, right?
Yes.
Exactly. Yeah. Cool.
Yeah. If your RPM doesn't drop much in the first couple of milliseconds, probably would work.
Yeah.
Nice.
There's a small range there.
Okay, I'm dry. I don't see any questions popping up in the chat, so why don't we hit the next question?
Okay. From Dan to all, I'm getting frightened. I think I'm beginning to understand some of this stuff. Oh, that's not the questions.
No. I don't know. I don't have the questions, so
Okay.
Steve, can you read it out?
I got him here somewhere. Hang on.
Yeah, just a sec here. Question number 2, are there any alternate materials that are acceptable for the accumulator end plates? Would nylon or puckboard work? Would they be mechanically workable? Is there a serious concern in this part regarding static electrical buildup and electrical insulation factor? Do they need to be less than fully rigid based on the design only, being anchored at the base to wood rather than the design fully framed and anchored at both the top and bottom with a steel frame? QEG has been faithful to the Witts design in this regard. Is there a reason for this? It's kind of like 3 questions in that one.
Yeah. Well, yes, it needs to be very rigid and very strong. If 2 reasons for that, it's pretty heavy. The core weighs as much as a man when it's fully built.
Like a
And the other reason is that you got that rotor spinning in there, and you need to have a rigid mounting surface for the bearings. You're talking about a gap of 0.010 of an inch or less between the rotor, spinning rotor, and the stator. So you want to make sure that stays put. Nylon and puckboard, I think, would be too soft. If you use something like a good quality phenolic, I guess there's 3 or 4 grades of phenolic that we looked at, and being an electronics guy, I've been working with that. The FR4 is actually what they make PC boards out of. So that's what brought me to that. I knew it was very rigid and also very machinable. You can tap it and drive a machine screw right into it. It's very rigid, and it's one of the best insulators. So that's why I went with that. I think Witts used one of the standard brown colored phenolic materials. But I don't know. I just wanted to upgrade it a little bit. I knew that the FR4 would handle it easily, and actually, half-inch thick is really plenty. I started looking at I think 5/8 was the first one I looked at, and it seemed to be a little bit overkill. So half-inch was a good compromise, but it's great stuff. And you can use any of the other phenolics as long as it's rigid. It does have to be rigid. And just to address the wooden base, that's just a prototype thing. We came up with that just so we could get it going pretty quick. What they did here in Taiwan was very good. Was ingenious. They bought well, it's similar to the FR4 material, but 1.5 inches thick, and they're using that for a base. And they actually do thread it and drill it and thread it and drive the mounting bolts right into the base material. And that worked out very well. But really, I would envision probably a tubular steel frame like you would have on a big conventional generator. This is definitely a prototype setup. So that's probably
Okay.
That's
So
that's funny because that's his second question. His second question is if they can actually build a full metal frame out of 2x2 tubing, if there'd be any effect on the core itself.
well. I don't think there would be any problem as long as the part that the core is actually mounted to would have to be an insulator, and that's because you have a high voltage in there, an inch away from the end plates. So I don't think you'd want metal there. But if we pay attention to spacings and do some testing, we see how far you could put a piece of sheet metal away from it safely. I don't think that would be a problem because a toroidal transformer, which is really what you end up with, the final thing in the operation of the device is just a standard transformer action. So, you don't want to have any magnetic materials too close or ferrous materials that could rattle. But yeah, just would take a little bit of testing and design. Metal frame would be okay, as long as it's not near the high voltage area. Yeah, not too near. But the toroids are self-shielding as far magnetic field problems. There shouldn't be any magnetic field problems. I think there was a question like that last time we talked, whether you could have two of them in close proximity. And to my knowledge, a toroid transformer is self-shielding, so it shouldn't be an issue. Just got to watch the high voltage.
Mm-hmm.
Yeah.
Cool.
So
I have a question on the end plates. Now, between Steve and Lisa or Matt, is there any possibility of putting a package together where they get the end plates in and actually bolt it all together, so with the spacers and everything, and it would increase the cost of the coil, but it'd be one solid shipping package, and everything would be lined up and stuff like that, right? If that could be a possibility.
Yeah, that sounds like a really good plan.
Mm-hmm.
yeah,
To have the end plates put on the core and shipped like that.
Yeah, with the rotor and bearings in place and everything.
Yeah.
Yeah, as one package. It would increase the cost, but it'd be more practical for a lot of people when they start out.
Sure would.
Yeah.
Yep.
I don't know. I'd like to be able to do a little bit of work on this thing.
Yeah, for sure. Well, there'd be an option. It'd be like package 1, package 2, package 3, or something like that.
Steve,
Oh.
this is my way of being funny.
All right, Ed, we appreciate that humor.
Yes, we do. Yes, yeah, we could have kits at different levels of completion.
Right?
Absolutely.
It's a little tricky drilling all the holes without a precise drawing. So yeah, that would be helpful in that case.
It could come with the shaft too, right?
Yeah,
Yeah. We'll have to talk to Matt.
yeah.
And Steve's here listening. What does he think?
Oh, absolutely. The way I would do this is through a CNC milling machine. It would be completely automated. Just put in the phenolic, and in a matter of minutes, you'd have a completely finished end plate.
Yes.
And as for the steel, mechanical steel, as soon as we have a proven one here, because we have to determine before we go to the progression die, it's 4 weeks from that date, we'll have a completely automated blanking progression die. Because it's already been designed, everything's ready to go. We just need Jamie to approve it, and then it's 4 weeks from that date, and we'll be blanking out. It's at approximately 1 a second.
Wow.
Cool.
Yeah.
Yeah.
That takes care of a lot of details. Yes.
Yeah.
In one fell swoop.
Absolutely.
Yeah, and I will review that and let you know about it as soon as possible. It's been crazy here,
I can imagine.
obviously, but we'll catch up.
Perfect.
We'll catch up.
Okay, Steve, any more questions?
Yeah,
Steve,
one more.
Steve Sager.
One more.
That was he pretty well answered the last question that I had there, unless I haven't got it pasted in here. Okay, yeah. And I think this was asked before. Can we use a wider range of caps and add more or less to get the same or close effect?
Yes, yeah. I think we talked about that last time, but yeah, it's good to have when you're tuning. It's good to have an assortment of capacitors around. Like I say, we zeroed in quite a bit better, I think, today on the final value. Of course, it's going to be different depending on well, the steel probably is the most very well. I don't know. The steel and the windings probably the most variable factors. Things like when you get it if you were to wind it by hand, um, you'd have less tension on the wire and less consistency. If you do it on a machine, it's likely that the windings will be tighter and cleaner, so your inductance is going to vary a bit, and that's probably the most variable component is the inductance. The first one we built was I think the total inductance was about 21 henries, and the last time we got one wound, it was closer to 27. So there's some variability there, and that'll affect the capacitor value. But there is going to be a lot of voltage across those capacitors, up to 25,000 volts, and the higher the voltage rating of each individual unit, the less you would have to use in a series string. So it's a little bit of a challenge. You could use, instead of, for instance, if you had like we have in the manual, a 2.5 microfarad at 2,000 volt, you could use two 1 microfarads at 1,000 volts, or pardon me, at 2,000 volts, which are a lot easier to find than a 2.5 microfarad. If you use two 1 microfarads at 2,000 volts in parallel, and then series those with the next pair, you can do series parallel combinations to get the cost down, definitely. But I think the most efficient way to do it is to have as high a voltage as you can on each individual capacitor. But that 0.125 microfarad value is probably going to be somewhere around there most of the time.
Cool.
Yes.
Hey, just another question. I was surprised to hear of all the progress since our last session that we had, because I thought you had to get the core rewound again. But was that not the case, or was it the case?
Well,
It's still the case.
yeah,
Yeah, they have
it's-
to get it rewound.
But you still got these results with something wound the wrong way.
Yeah. Well, the direction of winding was correct. The direction was okay. It's just that the start and finish on one coil was transposed.
Oh,
Yeah. And that's not good, because you have a higher voltage. If you do it that way, the voltage at the core is going to be higher than if you have both starts in the proper orientation.
okay.
It works, but we've had some. If we push it too hard, it starts arcing. So
Yeah.
you get up to about 4.5 amps.
And that's strictly because of the positioning of the input and the outputs.
Well, yeah, and this. Well, if you're a toroid winding company and somebody brings this core to you to wind, it's going to take a couple of tries, a little bit of experience to get it wound as cleanly as possible. Like when we got it back the first time, they rewound both coils, and one was better than the other. So, and this was the first time these guys tried it. So, that happens a lot. If you have to get used to doing it. It's pretty large and pretty heavy. So, it takes a little practice at even at a professional winding company. It takes a couple of tries. But where I was going with that is one of the coils is bigger than the other, so you have to be careful. Yeah, one of the important points is that you have to have like a 1/4 inch between the surface of the windings and the rotor bore. Have some spacing in there, or it will arc, because there's a lot of voltage there. And if you have an arc on the surface, it's not going to kill the generator, but eventually it'll break down. If you had a short within the coil, then you're done right away.
Right.
But on the surface, it will hold up for a while. But progressively it'll arc more and more. Really, the whole, we're convinced that the whole trick to this thing is how you build that core. And Witz even said that. But that's the tough part. We've kind of been from a couple of people we've talked to, it's looking like the right way to do this thing is to vacuum impregnate it. Build the coil without interlayer insulation, so that you can keep it as small as possible, and then just dip the whole thing and pull the air out, and it'll suck the epoxy right into the windings, and that's the way to do this thing.
Awesome. That's cool. And that can just be incorporated into the manufacturing process.
Yes.
Right. That's right. Now, Kevin came late today, and he would like you to back up a little bit, I guess, and tell the good news.
Hi, Kevin.
Hi, Kevin.
Hi, Ange. Yes. Okay. Well, I guess the main point is that we discovered that we were really thinking about this thing the wrong way. And even though we've had some problems with arcing and insulation problems, the thing is, we were in the victims of thinking about it the same, in a mainstream kind of a way also. But it turns out that it's not going to give you 40 amps at 230 volts. It's actually a high voltage generator.
Hello? What happened?
No, you're still there.
Oh, okay.
Oh, good. Okay.
Wow.
Um,
We lost the picture.
Well, your sound is good and your picture's good on my end, so.
Okay.
we're back. I think we're back. Yeah, we can hear you okay.
Share everything from this call, right?
Yeah.
Yeah, we can hear.
Okay, so we were trying to figure out, okay, how do you actually go about tuning this thing and getting the output where we thought it would have to be. We're thinking of it as like a conventional generator. If you go to Lowe's and buy a generator, it's going to be 240 volt or 120 volt at whatever amperage you're buying, 20 amps or 30 amps, for your wattage. But what this generator actually does, it probably, when it's perfectly tuned and optimized, you're not going to get any more than 10 amps out of it. But you might be able to get 2,000 volts on the output. When we were originally testing it, I was a little bit mystified because I noticed that when you're in resonance, if you increase the motor speed, the voltage just starts shooting up. I mean, I saw 500 volts on the output, and it kind of made me a little nervous. Like, how high is this voltage going to go? And I just assumed that, okay, well, we have to regulate it and we have to keep it down. But no, it's designed to put out high voltage on the output and low current. If you have 10 amps and 1,000 volts, those are 10 kilowatts. And it creates a little bit of a challenge on how you interface it to your home or whatever it is that you're trying to drive. But the inverters that we've been talking about are good up to like 600 volts input, DC input. And if you talk to an inverter company, they could probably customize that input easily. I'm an electronics guy, and I've designed several solid state motor drives, and it's not a hard thing to do to build to modify the input of one of these inverters to be able to handle 1,000 volts instead of 600 or even 2,000. And of course, it takes care of all the rest of it for you. The inverter, you can select the output voltage and frequency, and it does the interface to the grid if that's the way you're going. And you could also do a transformer, a standard transformer, just like the one that's hanging out on the pole in front of your house, is designed for high voltage input. So you could do a step down, step the voltage down from 1,000 to 200 or 230, and the current goes up. So it wouldn't be that hard to interface it. I'm going to, as soon as I get some time, I'm going to look at trying to modify one of these inverters to take a higher input voltage. It's really everything, the tuning and all the stuff that we were mystified with before begins to make sense now.
Yeah.
And one of the things is the exciter coil. People have been having trouble getting it to resonate. In fact, I don't know of anyone who has been successful. I haven't been told about anyone so far, but okay, if you're trying to get the thing to resonate at 300 volts, it's going to be very difficult. But if you double that voltage, that thing's going to start ringing. So, if you have 600 volts across that coil and that little gap, it's going to start. You're going to have a little plasma in that gap.
Plasma.
Yes.
You just have to let it work like it's supposed to instead of holding it down.
Yes. And let it go up.
That's right.
Now let that voltage rise.
Yeah.
And
So I want to say that we're going to let Mr. Lee close up shop here. We wanted to have this call tonight because we're leaving for Morocco tomorrow, and they have very bad internet connection. So I'm not sure we're going to be able to connect, but we'll keep in touch in the private chat room. And if we think it'll go good, then we'll have another call. But just in case we can't do that, we wanted to make sure that we got on tonight. So that's all I wanted to say.
Yeah. Just be sure and keep in touch, because there may be ways to do it by phone or just audio if you have a chance.
Yeah, maybe just audio would work. I know that every time we've spoken to Brian or Heather or Dee over there in Morocco from the United States, it's been terrible.
Yeah.
Terrible. Can't keep a connection. And it's been either on the phone or Skype. So just a heads up with that.
Okay.
And we'll be, gosh, there were 80 people coming to Morocco for this.
Yes.
Yep. And there's, yeah. And we're going to be there for a full 2 weeks. So we should have great news. And at the same time, these guys are going to get their cores rewound. And we'll be working alongside everybody.
Yes.
Because we're all in this together, the human race, and we're gonna do this. We're gonna be successful.
Yes. We will prevail.
Yeah.
We will prevail.
QEG team. Yay.
Go, man, go.
Ed, is there a way that I can put up a video on here?
Yeah.
Yeah.
You just have to open it up on your
Oh, right.
on your screen.
Let me show you this video.
It might take a minute to load, but I tried that already on my end, and it worked fine.
We got the information about the
This is, and she'll say who it is. Okay, so I do that.
Now share your screen.
Share the screen. Here we go.
This is a reaction to lovely ladies when they got the information about the QEG. And this was in Vienna. Yes!
That's all I wanted to share. I thought that was great.
Fantastic. Fantastic.
Okay, I'm going to stop the recording now.
Okay.